Good morning, students. It's 5.5, bases other than e, and now we're going to be integrating. Start off with something that you need to memorize. Put it in the memorization box. Integral of a to the u du. I love this formula. It's golden. All right, so here's the deal. A to the u is an integratable, u is a differentiable function of x, and a is a real number other than 1. What you get is 1 over the natural log of the base to the power plus c. You'll notice that there is no u prime. There's never a u prime with integration. That's all taken care of with the u substitution that you go through at the beginning. All right, let's take a look at a few examples rather. How about 5 to the cotangent of x times the cosecant squared of x dx. All right, you've got a product, you've got quantities other than x raised to a power, a lot of things happening in this problem. However, the thing that you should key in on is the fact that you've got a numeric base raised to a variable power, something other than just x, so the odds are good that the exponent is going to be u. Now, you should also think about the relationship between u and du, and if in fact it does give you what you need, and it does here, the cotangent then derives to the negative cosecant squared of x dx. I need the cosecant squared of x dx. I don't need the negative. We'll divide both sides by -1. And now I'm ready to go. This is going to be 5 to the u. Cosecant squared x dx comes out, and negative du goes in. We move the negative out front because it is a constant multiple. This then gives me a final answer of negative 1 over the natural log of the base to the power. The power is cotangent of x plus c. And that is your final answer. All right, here's another example for you. 7 to the log base 3 of x, all over x. If you let the denominator be u, unfortunately you don't get anywhere close to what you've got in the numerator. And again, what you're looking at here is a numeric base raised to a power. A good place to start is by making the power u. Now, if you recall from earlier in 5.5, when I derive a log with a base other than e, what I get is 1 over the natural log of the base times 1 over what I'm logging times the derivative of what I'm logging. The dx then comes to the other side, putting the derivative in differential form. I need 1 over x dx. I don't need the ln 3, so the ln 3 can come to the other side. This gives me the natural log of 3 du is equal to 1 over x dx. All right, taking these 3 lines here and putting them into the original gives me 7 to the u, right? Because u is log base 3 of x. 1 over x dx then is equal to the natural log of 3 du. I'll take this portion out front just to get it out of the way. This gives me then the natural log. This gives me the natural log of 3 times the integral of 7 to the u du. Again, constant multiples can pass through the integrand. This then will give me a final answer of the natural log of 3 times 1 over ln 7 times 7 to the u, that's log base 3 of x, plus c, and that is my final answer. All right, as you work through section 5.5, you'll notice that you're going to have problems mixed in from earlier in the chapter, as well as some problems thrown in from chapter 4. So don't forget those formulas, and this will give you good practice at that. If I take a look at this, let's see here. If I let 6x be u, that's not going to get rid of the quotient. I'll have 7 to the u over 4 plus 7 to the u. It's not going to work. Also, I cannot split denominators. So if you have a sum or a difference in the denominator, it is not splittable. If this function were flipped upside down, absolutely you could split it. So how about this? If I think about the relationship between u and du, let's just let u be the denominator, because I do have a formula for integrating 1 over u. This is 4 plus 7 then to the 6x. When I drive that line, 4 goes to 0, 7 to the 6x goes to the natural log of the base to the power, times the derivative of the power, and then again I'll move the dx to the other side. What you'll notice here is ln x and 6 are both constants. These can go to the other side with division. This is going to give me 1 over 6 ln 7 du is equal to 7 to the 6x dx. So using those lines there, I can take the original integral and I can use substitution. This is going to give me 1 over u, and then 7 to the 6x dx turns out to be 1 over 6 ln 7 du. The 1 over 6 ln 7 can come out to the front because it is a constant multiple. That's 1 over u du. And again, we have a formula for 1 over u du. This turns out to be 1 over 6 ln 7. That's the constant out front. 1 over u is the natural log of the absolute value of u, which is 4 plus 7 to the 6x plus c. And that then is my final answer. All right, one more quick just tip that might help you through this. Just some similarities, right? If I take the integral and I have a to the u du, or if I just derive with respect to x a to the u. All right, the first one, as we know, is going to be 1 over the natural log of the base a to the u plus c, whereas if I derive, I get the natural log of a, that is the base, a to the u times u prime. So similarities and differences here. You'll notice that the deriving does have the u prime because of the chain rule. There's never a u prime again when you're anti-deriving. But it's the constant out front that I want to call your attention to. You've either got natural log of a or 1 over the natural log of a. So I kind of think of this integral here as being an s to remind me to sync the natural log. So when you integrate that, that drives that natural log to the base, whereas when you're deriving, you keep it up top. I don't know if that's helpful, but you can use it if you like. All right, people, that should be enough to get you through the section. Thanks again for tuning in. Talk soon.